Finally, the other case study is thermal management, which is the last case study in this particular project, and belongs to the thermal management. And again, currently the vapor chambers are produced by sintering techniques, where the copper powders are sintered inside the vapor chambers in order to induce the capillary action. And due to the sintering process, the porosity is variable, and poor reproducibility arises from this variable porosity, and due to that we have inefficient heat spreading on the surface, along with temperature non-uniformity. So the conventional wicking also has multiple steps involved in the process, and this is also energy intensive since sintering process is involved, and also it is difficult to tune for different geometries if you want to optimize the structure and optimize the capillary and heat transfer properties on the surface. So with the laser surface texturing, we wanted to create different micro and nano wicking structures on the metallic surface to replace the wicking sintered wicks, which are intended to enhance the capillary flow and the nucleation site density on the surfaces, and also increase the heat transfer on the surface. So the key performance indicators and key objectives are shown here. So our aim was to increase the water transport, which is the capillary water transport inside the channels, by 30%. And with this, we can achieve up to 48% improvement in the cooling efficiency with the redesigned vapor chambers with laser surface texturing. And also the main aim is to replace the conventional sintered or powder mesh surface treatments with the hierarchical laser surface texturing. So in this slide, we can see the vapor chamber along with the heat pipes as shown here, and with different techniques such as femtosecond laser processing and nanosecond laser processing, we have generated wick structures on the inside inside surface of the copper vapor chamber. And on the right side, you can see that with the femtosecond and nanosecond processes, we have created different structures, different pillar structures inside the surface, and we have tested it for the capillary action as well as the heat transfer, which I will show in the next slide. So this slide shows the capillary performance of the top and bottom plates. Actually, the vapor chamber has both top and bottom plates, which are separated by the spacers, and the top and bottom plates both are textured and tested for their capillary action. The top image shows the nanosecond laser texture plates, and the bottom image shows the middle image shows femtosecond laser texture plate, while the last image shows the commercial commercial sintered wick plates. And the capillary performance, what we understand from this particular use case is both femtosecond and nanosecond laser texture plates perform akin to the commercial wick plates. At the same time, when we tested it on the bottom vapor chamber bottom plates, we understood that we can achieve more than 30% reduction in the capillary rise with respect to time on the vapor chambers. And when we tested these plates with respect to the heat transfer, we also achieved there are some of the tests, some of the assembly techniques we have done before testing on the vapor chamber. Both plates are initially laser patterned, and support pillars were added between the both laser plates, and the plates were laser welded and filled with vapor chamber liquid, and finally tested for heat transfer. And when we tested with vertical heat transfer, vertical spreading here test rig, we have understood that the temperature difference between the top and bottom plates along the VC and through the VC is reduced by more than 48%. The red color graph here shows basically the commercial vapor chamber, and the green one shows basically the laser pattern vapor chamber that shows significant improvement in the temperature difference between the top and bottom plates. So in summary, as I mentioned, in the automotive use case, we have achieved 20% target pressure drop with the hierarchical textures. We also demonstrated anti-scratch and antimicrobial properties at the coupon level, and the demonstrator molds are prepared with the SYNTECS machine and ready for injection molding. In medical use case, the target adhesion and frictional properties were achieved. Also, multiple treatment steps were replacement of multiple treatment steps were demonstrated, and finally the demonstrated cups and stems are laser textured on the SYNTECS machine, and they are ready for poro coat application as a final step. In the thermal management use case, we have seen that 30% improvement in the warp transport with the nanosecond laser surface texturing, and also we have demonstrated that we can replace the commercial conventional wick sintering with the laser surface texturing. And also 40% improvement in the heat transfer also demonstrated with the laser textured VC plates with the vertical heat transfer rig for PC graphics card and applications. Yeah, so this is the end of my presentation. If you have any questions, I would like to take.
Thank you, Anvesh. Let's see if there is any question in the chat. Nothing. I have a short question. So, do you think that would be needed further validation or more testing to prove the industrial adaptation of these technologies in these case studies?
Yes, especially in case of medical, we need more testing because they need to be approved by the appropriate regulatory agencies. But in other cases, possibly we can scale up the process with sufficient within less time compared to the medical use cases.